Hi, in this video I'd like to provide a overview of what we've been doing with regards to cam design. The first thing is a description of a cam, which we've gone over pretty much, but just recall that a cam is a part of a mechanical system, and the idea is to produce some type of cyclic motion. So I can either drag my mouse back and forth and see that the follower is going to go back that cylindrical cam, or we have a plate cam, which is mostly what we've been dealing with right now. And as the cam rotates at a particular angular frequency, the follower is going to move up and down. All right, so we have two different types of motion cycles that we're mostly interested with. And with regards to linkages last semester, you had continuous motion, though you did deal with building dwells inside of it. Cams are expressly made to provide a type of motion where the dwell is expected. So we have a single dwell motion, so the follower will rise, dwell in a location, fall, and then immediately begin repeating again. Or we can have the double dwell motion, which is what you've done in assignment 1, where the follower rises, delays for a moment in what we refer to as high dwell, then it falls, low dwell, and again we continually repeat. All right, so these are the two different types of cam displacement profiles shown. So what we're looking at here is we're plotting the position, or the displacement rather, given as s over as a function of theta. And we're going to say that we start from some zero displacement up to a displacement, maximum displacement of h. So we have some sort of function which is as of yet unspecified, moving the follower from 0 up to h, will dwell for a certain period of time, some specified amount of rotation, where 2 pi is a full rotation of the cam, and then we would fall. And if it was a single dwell, we would immediately go back into the rise function and repeat. Whereas if we have the low dwell, the double dwell function rather, we start with a low dwell and go through the rise, high dwell, again go through the fall function and repeat. So now we can often think about, in most of the equations that we've been looking at, we are always utilizing our functional dependence of displacement, velocity, acceleration, and jerk as functions of theta. But if we are assuming that we have a constant angular velocity, then theta is just omega t, where omega would be constant. So if we wanted to, we could always convert our equations to being functions of t just by dividing through the angular position variable by the constant omega. So this really permits us to describe the motion equations using either theta or t as the independent variable. And the textbook in their description, which I'm following, utilizes theta as the independent variable. So what is our design problem that we've been looking at? So we have required displacements and timings that somebody is going to give to you, and then we want to develop a cam profile that's going to be able to achieve these parameters. So the kinematic parameters of interest, as I just said, are displacement, velocity, acceleration, and jerk, where the velocity, acceleration, and jerk are successive derivatives. So this is the first derivative of position, the second derivative, and finally the third derivative of position. And we can express these. Here are the equations expressed as functions of the independent variable time, and here they are expressed as functions of the independent variable theta. So jerk is a new kinematic variable that we don't often see in terms of our standard Phys 1 classes, or even in our sophomore dynamics classes. So I just love the term jerk, but as Wikipedia says, it's also jolt, surge, or lurch. So if anybody's ever driven a standard shift car, and when you get that jerky motion back and forth, that is because the acceleration is changing. You're not doing a smooth change in your velocity over a function of time, which would be a constant acceleration. So we then, with that established, we can go on to the fundamental law of cam design. So any cam is designed for operation, so other than very low speed. So that make the point that you could have any shape plate, even with sharp edges on it, and as long as you are willing to rotate it at a relatively slow rate, 1 revolution per minute, anything is good to go. But as soon as you start getting up to hundreds or thousands of revolutions per minute, the vibrations that would be induced by having any discontinuities in these functions start playing a major role. So the idea for this fundamental law of cam design is that the cam function must be continuous through the first and second derivatives of displacement across the entire 360-degree interval. So the first displacement of the first derivative of displacement is velocity. The second derivative of displacement is the acceleration. And then the second part of this fundamental law is that you want the jerk to be finite. So there can be discontinuities in the jerk equation, but across the entire 360-degree or 2 pi interval, you want the jerk to be at least finite, and displacement, velocity, and acceleration must have no discontinuities in them. All right, so we'll end the first portion of this video here with just sort of a follow-up slide, or something that kind of gives us a full idea of what it is we're looking at. So as a designer, you might be given different values for the time that you want something to rise, the time you want something to dwell, as well as the timing for the fall. So these may all be, I'm showing them as being essentially 1/3 of the total cycle of 2 pi, but that's not necessarily the reason. There's no reason for that other than by convenience for the diagram. So you might be asked to have something rise very fast, dwell for quite a long time, and then maybe fall at twice the rate or half the rate of the rise. So the dwell is well specified. You're going to dwell at some vertical position or some total displacement from 0. So we have h, 0 up to h, and these stars are specified locations, right? We know that we're going to start at theta equaling 0 at the position at the follower at 0, and then at some point theta equaling to something, you're going to be at position h, and you're going to be there for a certain angular rotation. You'll still be at h, and then after you finally go through the rest of the cycle, you'll be down here back at h. The red and green dotted lines here are meant to indicate that we don't really know what these functions are, and of course that is what we're trying to design for, which I'll pick up in the next video.